Hello everyone and welcome back to the channel. So it's actually been a very long time since I've uploaded any videos on this channel, and though I was trying really hard to create some content, record videos, but things actually got really hectic on both professional and personal front for me. But now that all the fires have been put out, I thought it's a good time again to start creating some more videos which you guys might find helpful. um, Before moving to the actual video, it's kind of an announcement or a FYI, whatever. So I was thinking that moving ahead, what kind of content should be uploaded on this channel. So definitely there are going to be interview experience videos and mock interviews and all those things, discussions, and in fact discussions on interview experience with Amazon, Google, and Shopee are coming up very soon. But apart from that, I also wanted to start small series or playlist on different topics. Now these topics could be anything within computer science, mathematics, like DSA or system design or machine learning, deep learning, combinatorics, or say linear algebra. Any topics which I think I have a good understanding and I'll be able to explain it well. And these playlists will be kind of a quick crash courses or say cheat sheets for you, which you can very quickly go through these playlists and get and ramp up on these topics whenever you want. So before your jobs, before your projects, or maybe before your interviews. So I thought that this kind of content would be a good addition. So this playlist on recursion is actually going to be the very first playlist of this complete series or initiative. And in this playlist, we'll talk about the concept of recursion, the intuition of recursion, and how do you map this intuition to actual code, and then how do you analyze a problem, the complexity of the problem, and what are the different types of problems that we can solve using recursion. We'll also see few examples and practice problems in this playlist. So without any further ado, let's start with our video. And today we'll be discussing about recursion. Now, what is the most basic or the unofficial definition of recursion? It states that a function calling itself is known as recursion. Now, you may think that why would a function call itself? If we see from a procedural programming point of view, what is a function or a method? It is nothing but a piece of code that is achieving some use case, and given a valid input to the method, it returns an answer for that method, or it performs some activity for that input. Now, without loss of generality, if I say that my function f works for a input x, then it would also work for a subset of this input y. And what I'm trying to say is that if it solves a bigger problem, and if I break this problem into smaller subproblems, my function should also work for these smaller subproblems. Now let's say I have a function, and function here is nothing but a function uh, from the point of view of programming. So it's a function or a method. So let's assume I have a function f, and given an input x, it gives me an answer, and I assume that this is the correct answer because this function works correctly. Now if I take an input y, which is a subset of x, and now I give y as an input, then I know that my function is going to return me an answer dash dash, which is going to be a different answer, and this answer is also going to be correct. And this is only valid when both x and y are valid inputs. Now if this is true, I can say that I can use this answer dash dash to calculate answer, because there are a lot of problems which can be broken down into smaller sub problems, and if we are able to solve those smaller sub problems, we can somehow aggregate the answer from each sub problem to calculate the answer of the complete problem. Now if this function is returning correct answer for a smaller subset or a sub problem, then I can find a way to aggregate all those answers of those sub problems and find the final answer. So this is the whole idea or intuition behind recursion, and why a function call itself. The function calls itself with a smaller input, a subset of input, or for the smaller sub problems, and once the smaller sub problems are solved, I get an answer for all those problems, or or an appropriate activity has been performed for all the smaller inputs. I jump back to the bigger input and I use the data or feedback from those smaller sub problems to achieve the final answer for my bigger problem. Now let's take an example. For instance, so one of the famous example is that of a factorial. Now we all know what is factorial x. It is nothing but x multiplied by x minus 1 multiplied till 1. Now this can simply be rewritten as x into x minus 1 factorial. Now if I have a method that calculates factorial given an integer input, and I say that method works for x, I can easily say that method also works for x minus 1. So why don't I delegate the duty to first calculate the factorial for x minus 1 to the same method, and once that method has calculated this answer, I have this answer, what is going to be the final answer? The answer is going nothing but x into answer dash dash. So I delegated the job to calculate the answer for a smaller input to the same method, and when I got the answer for my smaller sub problem, the task was nothing, because I just had to multiply the number and return it, because my smaller sub problem had already been solved. I don't need to worry about that. Now at first look this might seem a little confusing, a very good intuition which comes in really handy with recursion, and this intuition will really help you initially, and kind of as you proceed this will become sort of a muscle memory, so you won't even think about it consciously, but then it does really help you, at least initially. So what is the intuition that I'm talking about? It is that when you have to write a method, say any dummy method, so what you need to say, what you need to assume is that this dummy method works for a smaller input. I don't care how it works, I don't know how it works, I just know it works for a smaller input. All you need to take care while writing this dummy method is that it works for a smaller input, and I need to use the answer from the smaller input to calculate my current answer. Now I don't have to care how it works for the smaller input, it gives me a correct answer. I have to use this answer and calculate my current answer. So this is the one thing that I need to keep in mind. And the second thing I need to keep in mind while doing recursion is about the base case. Now what is a base case? If I say that a method keeps calling itself, won't it be a kind of an infinite loop? Because the method will keep calling itself for a smaller subproblem, smaller subproblem, smaller subproblem. So there has to be a check which tells you that the method does not need to call itself. So that base case is basically a check that you have reached such smaller subproblem that you know the answer, and you don't want to call the function again for a smaller subproblem. You will directly return the answer from the base case, and that base case will basically break the infinite loop. And once you have returned the answer for the smaller subproblem, you'll keep moving above in the ladder, and the answers for the bigger and bigger and bigger problems will be calculated as you move above in this ladder. And in this dummy method, from the base case you have stopped the infinite loop, and in this dummy method, once you receive an answer for your smaller subproblem, you don't have to care how that answer came, what happened. You just need to care about this step, that I have the answer for this smaller subproblem. At this step, what should I do with this answer to get the answer for this stage, and then return that answer. So these two things, if you keep in mind while doing recursion, it comes in really handy initially. Now another important thing in recursion that or a visualization tool is a tree, is the recursion tree, which is really good to visualize the problem, and it is really good in analyzing the time complexity of the problem, because you're able to see what actually is happening in recursion. Because recursion, when a function call itself, it can become really messy. with the tree it becomes really easy to visualize. So in this tree, the node represents the problem and the child of each node represents a smaller subproblem. So let's try to draw a tree for factorial. Now I need to calculate 5 factorial. So my first problem is 5 factorial. What will be the child for this problem? It will be 4 factorial because I want answer for a smaller problem. Now for this it will be 3, for this it will be 2, and for 2 it will be 1. Now I know that 1 factorial is always going to be 1. So this kind of becomes the base case that I was talking about. Below this, we do not need to call this method again with a smaller input because we know that once we reach 1, always the answer is going to be 1. So this will return 1. Now once it has written 1, I know at this stage I've got the smaller answer. Whatever is the answer for the previous stage, I simply need to multiply 2 and return the answer. How do I calculate the answer for this stage? Whatever answer I have got from my earlier stage multiplied, this will be 1. So what I know that whatever answer I have got from the earlier stage multiplied by the number itself will be the answer. So 2 into 1, which is the answer from the earlier stage, multiplied by number itself will be the answer for this stage. So on and so forth. So I know that using the answer from my previous stage, I assume that the correct answer is coming. I use that answer, and from the current stage, I just know for the case of factorial, I need to multiply the number to the answer from the smaller stage, and I'll have the answer for this stage. So that's how you draw a recursion tree. Now in this recursion tree, because to solve the problem of 5 factorial, I just need to solve 4 factorial. But there might be a case where you need to solve 2 subproblems to be able to solve this problem. So let's assume that you were given an array and you need to find an answer. You need to search basically if a term exists in this array or not. Now if you are using recursion, a logic might come to your mind, why not I break this array into 2 smaller arrays and try to check if my answer is in these 2 smaller arrays. Similarly, I'll break it into 2 halves again, and I'll try to check. Now the base case could be that when the size of the array is 1, you can simply check if the only existing element is equal to the element you're trying to search and return an answer from here. Now using the answer from these 2 subproblems, you can see if you were able to find answer in any of these subproblems, you know that the answer for this subproblem would be true. But if both these subproblems return false, it implies that this element was definitely not there in this complete array, so this will also return false. Similarly here, and depending on the input from depending on the result from this level, you can easily calculate the answer for this level, for the original array, because if any of this was true, then the element was found, otherwise the element was not found. So as you can see that the recursion tree can have n children, and n can be each node can have n children, and n can be any value. And there might also be a case that in a recursion tree that a certain level has 3 children, the next level only has 2 children, or this level has only 1 children. So our calls for the subproblems can also be based on conditions, and depending on the condition we are making calls. So it is not necessary that every time a node will be making every node will be making same amount of calls. That can depend on an if condition which might be calculated based on the input. Now one thing which might be coming to your mind, that to solve a problem we are breaking down into subproblems, solving the subproblems, and then aggregating that answer somehow, or using that answer somehow to calculate our actual answer. Now this might seem quite similar to divide and conquer paradigm, and actually a lot of divide and conquer algorithms use recursion to solve themselves. But Yeah, so it's a question for you. Can you think of an example where you're using recursion but it's actually not a divide and conquer algorithm? Probably you can give your answers or comment your answers in the comment section, and I think it'll be a good discussion. So you don't have to worry if you don't have an answer for this question right now, because it is highly unlikely that someone is going to ask this question in an interview. It is just for fun or to understand things better, and we can probably have a discussion in the comment section. So just let me know if you can think of any example. Now we have understood the concept of recursion as such. Let's try to solve a problem and write a code for a problem using recursion. Now let's start with factorial only, and we were saying that we wanted to calculate factorial, x factorial. So let's assume that there's a method that returns an integer value, and the name of the method is factorial, and it takes input as x and it calculates the factorial of x. Now let's use our intuition, the intuition we discussed above, to get the answer for this question. So we know that, let's assume that the answer is, now we know that, or we know our intuition that we have to always assume that this method is going to work for a smaller problem. So let's call the method for a smaller problem, and we know that this answer is going to be correct. We don't have to worry about. But once we have received this answer, all our duty is to calculate the answer for this current stage. Once this answer has been calculated, this answer is correct, we know we don't have to worry about it. Now once we have got this answer, all we need to do is multiply it by x, because factorial for x minus 1 is going to be correct. And once we have got this answer, what we need to do is to multiply it by x, because that is going to be the correct answer, and just return that answer. So assuming that our method worked correct for a smaller input, we just use that input to calculate the current stage and return that answer. The second thing we had to keep in mind was the base case. So our base case, as we discussed, would be when x is equal to 1, I can simply return 1, because factorial of 1 is 1. So this method, let's do a dry run. We used a simple two-step intuition to create this method. Let's do a quick dry run to see if this method works fine or not. So I am calling this method with an input 5. So x is equal to 5. Now you know that we have something known as a stack, a function called stack. What happens in a function called stack is that whenever you call a function, a new element is created for that function call, and as you keep calling a method, a new element keeps on coming at the top. And when once you have reached the base case, it will start popping out those elements, and the elements which are popped out are in the order of last and first out. So that's why it behaves like a stack. This function stack behaves like an actual stack. So when you have called this factorial method with x equal to 5, what will happen is that an element will be created with f of 5 in this stack. Now x will be 5, and we'll land into this method. Now at first step, the if condition would not be satisfied. So what will happen next, it will move to this particular step, and again we know that this method will be called for a smaller input. So what will happen, a new element will be created for x equal to 4. Now again 4 will land in the same function. If condition will not be hit, will come on this step, the method will be called for a smaller input. So f of 3 will be called, then f of 2 will be called, and then f of 1 will be called, right? Now we simply know that when f of 1 is called, this if condition would be satisfied, and we'll not make any further call, and we'll return 1 simply from this position. So from here 1 will be returned, and this element will simply be popped out. So basically 1 was returned from here. Now when we are here, the answer will be basically the answer which was returned from the previous stage, that is 1, multiplied by x, which is 2. So which will be 2, and from this stage, and then this answer will be returned from this stage. So basically what will happen is that this will be popped out, and from here, from this stage, 2 will be returned. Similarly, when we reach x equal to 3, it will basically it will calculate answer is equal to the answer from the previous stage, 2 multiplied by x, so which is equal to 6. So 6 will be returned from here, and this will be popped out from my stack. From here we'll again return 6 into 4, which is basically 24, and 24 will be popped out, and f of 4 will be popped out from the stack. Again from this, now this finally we'll reach this stage, and this stage will basically return 6 into 4 into 5, and this will be popped out from the stack. And once we return from here, we'll be returning to our main function from where we called factorial 5, and we can see that our factorial has been calculated correctly, which is 120, and we'll get the correct answer for our method that was called. This is basically the main idea how recursion works and how do you write functions for recursion. We'll be writing a lot more functions, and we'll be solving more problems as we move ahead to understand recursion better. This is very basic idea of the concept and the intuition behind recursion. If you've just started, this is the first time you're seeing recursion, based on this video you're not at all expected to be able to write recursive functions. This gives you a very basic idea of the intuition and idea, but yeah, moving on from the next videos, we'll be able to write recursive functions. So another important thing that we should discuss here is that when you hear the word recursion, you kind of know that it is derived from the word recurrence, and recurrence relation is nothing but again a relation between a bigger problem and a smaller problem. So every recursion can actually be represented as a recurrence relation somehow. Let's say that for the factorial only, that f was my relation, then f of x can easily be represented as x into f of x minus 1. So this is nothing but a recurrence relation. Another example is that when you think about Fibonacci series, so what is f of n? F of n is nothing but f of n minus 1 plus f of n minus 2, right? So this is nothing but again a recurrence relation. So you see that any problem that can be solved by recursion actually can be represented mathematically by a recurrence relation. When we code, we are doing nothing but actually mapping this recurrence relation to the code, and these functions which are being called for a smaller subproblems are nothing but recursive calls that we are making. So this actually is a recurrence relation, and this is nothing but a recursive call that we are making is nothing but this function in the recurrence relation. Why am I discussing this? Because at times it becomes the problems become really hard, and if we are able to write a recurrence relation for a problem, it kind of becomes relatively easier to write the code for that problem. And this recurrence relation is actually really useful in coming up with the dynamic programming approach, something known as dynamic DP, which is used to optimize your recursive codes. So if we are able to write this recurrence relation, it is really easy to come up with a DP approach for your recursive code. So another very important thing that we need to keep in mind while using recursion is this concept of directed acyclic graph, or DAG. The concept is that if a problem can be modeled as a DAG, then only we can apply a recursive solution for that problem. If it cannot be modeled as a DAG right away, we have to try to somehow model it as an acyclic graph. Now I won't be explaining that what is a directed acyclic graph right now, because that would be a lot of information overload and we'll be jumping ahead. So I'll keep this point noted, and when we are doing graph, I'll explain in the introduction video that what is a directed acyclic graph. So I guess that's it for the introduction video of recursion. Hope you liked it, hope you learned something new, and I know there are going to be a lot of doubts. So please feel free to post all your doubts in the comment section, and I'll try to address as many doubts as possible. So I guess with this we can end this video here. Goodbye everyone, take care and keep learning.